So which one do you have a question on? You didn't turn yours in already, did you? No. Okay.
$48.
48. Let's make sure I've got the right 48. You have 1 kilogram of copper and want to make a practical solenoid that produces the greatest possible is that the right one? Doesn't sound right. Let's try a different 48.
621.
Oh, on page 621. At T equals 0, the current through a 45 millihenry inductor is 50 milliamps and is increasing at the rate of 115 milliamps per second. What is the initial energy stored in the inductor? How long does it take for the energy to increase by a factor of 5 from the initial value?
I get the first part. I just didn't know how to do the. How long does it take for the energy to increase by a factor of 5?
Okay, well, let's yeah, the energy stored in a magnetic field is 1/2 Li squared. Okay, so what is the inductor? 45.0 times 10 to the minus 3 times, what's the current? 115 milliamps? 50.0 milliamps. Squared. Okay, so somebody with a calculator, do the arithmetic. What's that work out to? 5.6 times 10 to the negative 5 joules. All right? Now, it says that the current is increasing at a rate of 115 milliamps per second. And it wants to know how long does it take for the energy to go up by a factor of 5. So what is 5 times that much energy? What's 5 times 5.6 to the minus 5? Point something? Oh, you're just jerking with me? I'm going to wait for someone with a calculator now. $2.8. Okay, times 10 to the minus 4 joules is now equal to 1/2 45.0 times 10 to the minus 3 times I squared, times the new I squared. So what we got to do is calculate the new I, the new current. It's going to be 2 times that divided by 45 times 10 to the minus 3. Comes out to I squared equals what? And then divide by 45 times 10 to the minus 3. That's after you take the square root?
Yes.
All right. So it's 112 milliamps. Now, the question is, how long does it take for it to get there? Well, it tells you that the rate, the current is increasing at a rate of 115 milliamps per second, right? And it started off at 0.05. It's now at 100.112 divided by 0.115. This is amps, and so it's divided by amps per second, which will give you how many seconds?
Get the 0.115.
That's the rate at which the current is increasing. At 115 milliamps per second.
0.54 if you round up, or it's like 0.539.
Is that so? It's like a half a second. Okay. Now, how many of you were looking to use that e to the minus t over tau? You know, the exponential equation for I equals I naught times e to the minus t over tau. What is tau? R divided by L? Right. Did they give you, anywhere in here, did they give you the resistance? Or did they give you the tau, the time constant for this inductor, this circuit? No. Big old honking red herring. Just straight linear unit analysis. Now, this same problem could have been worded differently and given you that kind of information, so you could have deduced the time constant of current changing in an inductor, at which point you would have needed to have known which one of those exponential equations to use. But in this case, nothing in there. There's nothing in there to intuit or to deduce tau, or what's the total current that's being applied, what's the total voltage applied, what's the, how is the, what is the peak current that is shooting for asymptotically. So when I worked through the problem, I quizzled over that for quite a bit, because Yeah, well, I'm working these problems first time just like y'all are, because this first semester I'm teaching this course, and I'm just using the course as it was laid out by the guy before me. So I'm working these problems for the first time too, and when I hit that one, that one stopped me. I stopped dead in my tracks and said, "Wait a minute." How do you get tau out of this? How do you find the time constant? How do you, this is, it's like, it's not a problem I would have even included in the textbook in this chapter. It's just a big red herring. So.
How long does it normally take you to work through all the problems you give us?
Oh, anywhere from a half hour to an hour. Why? No, this one took longer because, it's like, wait a minute. I also have to slow down and stop and make sure I get it right because, otherwise it's real embarrassing when I mark one of your papers wrong and you come back and say, but I did this right. And it's like, oh, you sure did. Look at me. I made a big mistake.
I'm sorry.
You were about to say something.
No.
All right, well. Does anyone else have any questions about homework? All right, well, let's do a quick review. This chapter, this test, I say chapter, it's actually 2 chapters. The test on Wednesday is going to cover all of chapters 20 and 21. So let's do us a bit of a whirlwind review. And I will tell you that the exam is going to basically be like the other exams I've given you. I'm going to have like 5 questions, maybe 6, I don't know. But they will be a sampling of problems from the chapter. So let's talk about what we covered in these chapters. First, we looked at magnetic fields. There's your magnet. The field what direction do those lines go in? What direction do I put the little arrows? Say again? No, north to south. The field points from the North Pole to the South Pole. Hey, you had a 50-50 shot, right? Okay, we also found out that when a current is flowing in a wire, that it will produce a magnetic field when you have an electric charge moving in a circle. In this case, let's say we've got a current flowing through that loop of wire. How does the magnetic field go? Do one of the right-hand rules. Which one? Thumb goes in the direction of the current. Fingers turn in the direction of the field. So the field is pointing through the loop this way. Y'all need to remember how to do this, how to figure out which direction the magnetic field lines are going. In this case, which side of this loop is north? Exactly. This is the north, that's the south. Now, we also talked about the force that a magnetic field exerts on a current-carrying wire. Here's your wire, and it's carrying a current I going in that direction. Here's the magnetic field, B. There's the angle theta between the wire and the magnetic field. Who remembers the force that that magnetic field is exerting on that wire? Times the length of wire exposed to the field, because it's actually force per unit length. But it's B times I times L times sine theta. It's the perpendicular component of that magnetic field. Which direction? Now, point your fingers in the direction of the current and then bend them in the direction of the magnetic field, and your thumb gives you the direction of the force. In this case, is into the board or into the page. If the current was going the other direction, then you'd have to have much longer fingers and arms than I do, but you'd end up with the thumb pointing out. We also looked at the force of a magnetic field exerts on a moving charge. If you have an electron or a proton or a dust particle that has a certain electric charge of static built up on it, and it's moving in a magnetic field, what's the force of the magnetic field exerts on it? It's Q, the charge, times the velocity of the charge, times the magnetic field, times the sine of the angle subtended between them. And what is the direction? Again, right-hand rule of thumb. Mathematically, it's always the interaction between the moving charge particle and a magnetic field is a cross product. This would be actually a vector cross product between this velocity and this magnetic field, which means the result will always be orthogonal to both of them. So they don't have to be parallel. Like right here, you could have, this is your magnetic field, and this is the velocity of your charged particle, but the cross product of them will always be either that direction or that direction, where it's at right angles to both of the initial vectors.
You said that's the equation for a particle in a magnetic field?
This is. But I'm saying now to find the direction of that force, you're going to again use this same right-hand rule of thumb. Except instead of having it going in a wire, you point your fingers in the direction that the particle is moving, turn them towards the magnetic field, in the direction of the magnetic field, and your thumb gives you the direction of the force. Again, this is assuming it is a positive charge. Same up here. If it's positive current flow, then the right-hand rules apply. What if this charge was an electron, had minus Q? Well, you would still do the same thing, but when you would just reverse the direction of the force. It's still going to be mutually perpendicular. It's going to be orthogonal to both of the vectors, but it'll be in the opposite direction. Anybody have any questions so far? All right. We talked about the force of we talked about the magnetic field produced by a long straight wire. Now, here we're just mapping out the magnetic field of the current flowing in that one loop. But we don't have any idea what the strength of that magnetic field is. If we're talking about an actual current in an actual wire, we can calculate the magnetic field produced by it at a point R away from the wire. Anybody remember it? Proportional to 1 over R. Mu sub naught over 2 pi times the current divided by R. What is mu sub naught? Somebody look it up. Is it -7? Do I need to say it out loud that you want this written somewhere on your card? Okay. Obviously, you're not going to have a question on every one of these problems. Okay, you're only going to have 5 or 6 questions that you have to work through. But I promise you're going to need to know this. Okay? So write it down on your card somewhere. Who remembers the force exerted on between parallel wires carrying current? We can calculate the force exerted on this one by the current in this wire. And we can calculate the force on this one by the current carried in that wire. This depends on whether the currents are the same. But what matters is, are both of the currents going in the same direction, or are they going in opposite directions? I want to make sure I follow along in the book because I don't want to forget something. Like, what did I just see here? Oh, yeah. Force between 2 parallel wires. When the currents are both in the same direction, the force is attractive. They're both pushing the wires together. When one current is going in an opposite direction, then they push each other apart. And there was a picture in the book. Was it? Maybe it was in the homework assignment.
think on a 571.
No, yeah, I see that picture. No, this is a different picture I'm talking about. There's a picture somewhere in here that I remember seeing it, thinking it would have been an interesting one to point out to y'all to look at. No. Well, I'm not going to waste a lot of time looking for it. If you see it, you'll spot it. It's a picture of two bus bars, copper bars that have bulges, little, they're coming straight down, but there's this one section where they bulge out from each other. Kind of like and it shows where they're clamped down to whatever they're mounted to. And they're electrical bus bars, and it's, you could tell what happened was there was enough current flowing that those bars got hot enough that the magnetic field of repulsive between those two pushed against each other and caused the whole bars to deform and bulge out like that. Again, just want to remind y'all, because it's going to be germane to your chosen career fields, these forces that we talk about are it's easy to stop thinking of them as real forces and just start thinking of them as numbers and a formula. But they're not. They are actual and real. They can and will hurt you, and they won't lose sleep over it, or they won't feel bad or anything.
How much current or voltage do you have to have for those actual bus bars to do that though?
It'd have to be pretty. This was mains current. This was some fairly significant current, because you'd have to calculate how hot would the copper have to get to go into a plastic state, phase shift from solid, not quite to liquid, but to that plastic intermediate state between them. And at that point, once you can, so whatever current would give you enough power dissipation in that copper bar to produce that temperature, that's how much current it would take. The magnetic fields are there the whole time with all the currents, so they're there pushing all the time. What happened in that case was they got hot enough that the copper became plastic enough for the deformation to happen. And I'm quite certain that whoever took the picture did so when they found it and said, "Look what happened, we got to change this." I'm quite certain they didn't just say, "Oh, look at that, that's cool, I'll put that in a textbook." All right. Solenoids. What formula? That is the B is a magnetic field. That's not a force. That's the magnetic field at a point R away from a wire carrying a current of I amps. If this is a wire and it's carrying a current I, then the B, the field, the magnetic field at this point R, is going to have this value. I divided by R times mu sub naught over 2 pi. What did we just go over? The force?
The current flowing.
Oh, that's the force right here. The force on a current carrying wire is the magnetic field times the current times the length times the sine of the angle between the magnetic field and the wire. In the case of the two parallel wires, the sine of, well, you would, but it'd be sine of 90 degrees, which is 1. So yeah, this is the force exerted on a moving charge or on a current by a magnetic field. This is the value of the magnetic field. Now, solenoids. Got a solenoid. It's a wire with many loops. Has a diameter, has a length, what is the magnetic field inside that solenoid? Assuming, ignoring the fringing effect at the ends, you're restricted to a region inside where you've got the nice, constant, stable, steady magnetic field is over L, where N is the number of turns over length L. How would you change that solenoid to eliminate the fringing effect of the magnetic fields at the ends? Anybody? What would you do to get rid of the fringing effect, the fringing magnetic fields at the ends? And in fact, get rid of all of the magnetic field outside the solenoid anywhere? Turn it into a torus. That's torus. Not the bull. Yeah, torus as in toroid, not Taurus as in the bull or the car or the zodiac. Who knows how to pronounce Ampere's name? So I know we all pronounce it Ampere. In fact, it would actually be pronounced Ampere. So if you ever go to France, you're going to want to know that, or they're going to be real offended that you didn't pronounce it right. I don't know if any of you know this or not. I'm going to take a little bit of a tangent here. If you've seen reports on TV about Americans traveling abroad overseas. How do they refer to us in like France and other parts of Europe? They call us ugly Americans. This is a little tidbit, a little trivia of language that you may or may not know. In Soviet Union, in Russian, who knows the word for red in Russian? It's krasnaya. Right? In fact, Krasnaya Ploshchad is the red square. Okay, the word krasnaya means red, but it also means beautiful in Russian. So for generations, we were insisting that we would rather be dead than beautiful. So isn't it kind of like just going along with what we were already saying, that they say, okay, so you're ugly Americans? No, not even a snicker, huh? All right. I don't speak Russian.
Oh, okay.
No. Boy, wouldn't that be fun?
Just starts teaching physics in Russian.
No, but I do like to study other languages. I like to, languages did not evolve in a vacuum. And what does our language have to do with mathematics? Other than the fact that mathematics itself is a language. Physics is actually learning to speak the language of mathematics. Why do they call our language English? Because originally it was the Anglish, as the angles, the radians subtended between rays or vectors. Anyway, you will all be well served if you pay some attention to language and how it evolves. Who can tell me the vowels in English? Who can tell me all the vowels? A, E, I, O, U, and sometimes, because Y is a consonant when, and it's a vowel when. Nope. Y is a consonant if it is the initial character, if the initial letter in a word or syllable. If it is at any other position in that word or syllable, it's a vowel. Now, who can tell me the other sometimes a vowel letter? Give me an example when W is a vowel. Nope. O is the vowel. But how about this one? CWM, cum. It's a word. It's a kind of valley. It's like a natural amphitheater that forms on the side of a hill. Where would you encounter this word in everyday English? Sure you have. Yeah. You encounter it probably every time you go home and your mama tells you to get your feet up off the floor so she can vacuum under your feet. Except in vacuum, the W has been decomposed back into double U's, which is where the letter W came from. Anyway, let's go back to physics. Ampere's law. Let's go to Ampere's law.
So before you did physics, did you ever want to do like speech pathology or like anything with linguistics?
No, but I'm an ordained minister, so I study a lot of languages when I study theology and scriptures. A lot of Hebrew and Aramaic and ancient Greek and Latin. Latin is a language as dead as it can be. First it killed the Romans, and now it's killing me. It's Latin is you know more Latin than you think, because English and pretty much all of the European languages derive from Latin. The Greek and Russian derive from the Cyrillic languages. Arabic, Hebrew, Farsi, these all derive from the Semitic languages, and then of course the Orientals, Chinese, Japanese, these all derive from the hieroglyphic languages. Can you tell me the difference between structured and inflected language? Inflected. No, no. No.
Possibly like facial
You're getting closer. Structured language, just like English, is very structured. The words mean what they mean based on how they're positioned in the sentence, in context. An inflected language is one where the meaning of the sentence is implied by the fluctuations in your voice when you say them. We have an example of it in English, an inflection, exactly. We have an example of it in English that it's called upspeak. Someone's asking a question when their voice goes up at the end. Okay? Unless they're from the Valley in Southern California, in which case you can never tell what they're saying. The Ampere's law. Some of the parallel components of the magnetic field along a closed path of little segments of length will equal mu sub naught times the current enclosed. And we used that law to derive the magnetic field of a solenoid and to examine how the magnetic field in that toroidal solenoid would behave. Of course, in order to do that, we had to kind of already know how the magnetic field looked. We had to know what it was shaped like so we could know where we could ignore it, where it would add together and become stronger. Torque on a current in a loop produced by a magnetic field. This is on page 575. If y'all are going to do any studying on your own, you might want to go back and revisit how this equation is derived. But we know that the torque produced on a loop of wire in a magnetic field is equal to the number of turns in that wire times the current the wire passing through the wire times the area that the wire encloses. I went through and showed you that even though originally in the book it's derived for a square loop, so that the area is just the length times 2 times that little half torque moment. But I showed you how we could that same formula would derive for any, or at least I showed you how it would derive out to be exactly the same formula for a circular loop, as well as a square or rectangular loop. And in fact, if you do the integration and you do the general case, it will always work out to the same for any arbitrary shape of loop. Where the sine theta is the angle between the magnetic field and the face of the loop. So if you have the loop looks like that, imagine a vector sticking straight out perpendicular to the face of that loop. And the angle theta here will be between that vector and the magnetic field. Okay? That's important. If you'll recall, we worked this out when we looked at the frame inside the magnetic field. When it had the vector going out of the board on one side and into the board on the other side until the face of it lined up parallel with the magnetic field, at which point the torque went to zero. Because the force was still the same, but it was pushing again, they were equal and opposite instead of in producing a torque. If you do any studying, you would do well to go back and revisit this part and how that equation was actually derived. Where this tau here is torque, by the way. Remember that. This tau is torque. No, I is current. This torque is equal to force times distance, or the moment where d is the moment of the torque, the distance the force is applied away from the axis of rotation. Okay? Now, so that if you have this loop of wire on that axis of rotation and we're looking straight down on it, if the magnetic field is producing a force in this direction here and a force in this direction here, this force times this distance is that amount of torque. This force times that distance is that amount of torque, and the two torques add together. If the two torques were going in opposite directions, they would counter each other. That doesn't happen in a motor, so. No, you would end up, and this again, they go through the derivation of this carefully, step by step in the book. But using this, you end up with that torque. Yeah, force times distance. It's not the same as work. But it is. It's torque. Yeah, I'm just showing you what torque means. This is what it's talking about. It's the rotational force. And that I don't want to say force times distance because this distance is actually what's called the moment of the torque. Now, that's where we ended it in chapter 20. Then we went on to chapter 21, where we started talking about induced EMF. And we talked about flux. Who remembers what flux is? Say again? I think you may be ahead of us a little bit. No, flux is B times A. It's perpendicular magnetic field times an area through which that component of the magnetic field is passing. Okay, so it would be written B A cosine theta. And it's basically if you get the plane, the area that you're talking about the magnetic field passing through, If you rotate it so it's parallel at 90 degrees, then none of the magnetic field is passing through that plane. The flux through that plane goes to zero. If it's perpendicular, then you get the maximum magnetic field passing through. Right. That's flux. Now, a changing magnetic flux will produce an induced current. And it will produce an induced current by inducing an electromotive force or a voltage. Book uses that script E for EMF. Electromotive force. That is the same thing as voltage. Volts are the unit of EMF, like newtons are the units of force. Meters are the units of length. Volts are the units of EMF. Okay? The EMF induced by a changing magnetic field would be minus the change in flux divided by the time, the change in time, by how long it takes for the flux to change. The units would be volts. So if it asks you if you're asked what is the induced EMF, the answer would be X volts. All right? Now, that means if you have a loop of wire and the flux is changing in that, passing through that loop of wire, this is the amount of EMF or the voltage that's going to be induced in that wire. Okay, it's an actual voltage induced into the wire, and that voltage divided by the resistance of the wire would tell you the current that would flow through that wire because of that changing magnetic field. If there are more than one loop of wire, if there's more than one turns in that coil, then this becomes N times minus delta phi over delta T. Now, you also will want to look at the electric generator equation, where that induced voltage in a generator, it becomes 2 times the number of turns times the magnetic field times the length times the velocity times the sine of the angle between them, which actually reduces to where omega is radians per second, or the angular velocity that the generator is turning at. Number of turns times the magnetic field. A here is the area of the loop of wire that's being rotated in the magnetic field. Omega is the angular frequency. It's equal to 2 pi times the frequency in hertz. Okay? And the voltage, the EMF, the induced voltage here will be changing as a sine of omega t. Okay? That means if you're asked for the peak voltage generated by this generator, it's simply NB omega times the area of the loop. If you need the RMS voltage, it becomes NB 2 pi F times the area divided by the square root of 2. Okay? The voltage at any point in time, if you were to plot it out as a function of time, would be that peak voltage times the sine of the angle, the sine of omega t.
The frequency will always assume it's 60 hertz, right?
Well, no, the frequency would be specified.
Unless specified otherwise. If it's not specified, are we supposed to solve for the frequency if we give it?
You might. Do you remember how to solve for the reactance? X sub C, X sub L.
For the most part.
Okay. Everybody stop and pay attention. I know we're running out of time, but you definitely need to hear this. I want to go through a very quick example of a kind of problem with you. I'm assuming y'all remember how to calculate reactances, how to analyze an RC circuit, find out the voltage, the current, the phase between them. Not yet. I'm hopeful. What is the equation for an inductor? Where A is the area of the coil. If you take and you wrap a wire up in coils, this is L, that's the diameter, pi times the diameter equals the area. No, that would be the circumference. Pi times the radius squared equals the area. Okay? N is the number of loops, the number of coils you wrap. What if you were told to take 28 gauge magnet wire? Magnet wire is wire that has a very thin coating of lacquer. It's negligible as far as dimensions of the wire is concerned, but it's an insulator that keeps the wires adjacent wraps or loops from shorting out against each other. So what if you were told it has some 28 gauge wire, magnet wire? 28 gauge wire has a diameter of 0.3211 millimeters, and every 1,000 meters of it has a resistance of 212.41 ohms per 1,000 meters. All right? That's for copper, a specific alloy of copper or magnet wire. You're told to make an inductor of 100 loops on a diameter of, 15 millimeters. What's the area? For the diameter of 15 millimeters, it would be pi times 7.5 times 10 to the minus 3 squared would be your meters, your area. I said I'm just making up an inductor. You're going to make an inductor that has a diameter of 15 millimeters. And you're going to make it out of 100 turns. So N is 100. Here's your area. How long will it be? If each turn is 0.3211 millimeters, the diameter of the magnet wire, then it would be 100 times this dimension would be your length. How long would that piece of wire be? Each turn would have a circumference of pi times the diameter of the inductor. And that would give you the length of the total length of the wire, N times that circumference. That would tell you how much resistance that piece of wire has. This is how you would calculate the inductance that that homemade inductor would have. Does everyone see how that would work? You would write, the mu sub naught would be the permittivity of air. If they give you a different mu for the particular core material, then you would replace mu sub naught with that mu.
On the test, if you wanted us to do that, are you going to give us like the...
I would tell you what mu, yeah. Yeah. Yeah, because I mean, you would have to go and look up all of the possible mu's of all the different possible alloys, and they, actually when you start getting into this kind of magnet design, that mu is not as fixed a constant as people think. It will depend on temperature, it'll depend on how much current, how much eddy currents are flowing in it. It'll actually change a little bit just by being put in use. Say two, I know time's up. Well, you've got 100 length. If you've told that you have 100 turns, each turn has a length of one circumference of the diameter. So if the circumference is pi times the diameter, then you would multiply that length times 100 to get the total length of all the wire. And yes, I would tell you, you wouldn't don't worry about trying to write down all the different dimensions and resistivities of the different materials and different gauges of wires and such. Thank you. Anybody else have homework to turn in? Thank you all. I will see you tomorrow for lab.